The normal distribution is the most well-known continuous distribution. Just to refresh, by continuous, we mean that it can take any values within the interval. So for instance, height is continuous because you can be 65 inches or 65 and a half inches or 65 and a third inches or 65.1 inches. You can be anywhere in the range. The opposite of a continuous variable is a discrete variable, which can only take certain values. So the normal distribution is the most well-known continuous distribution, and it does a whole bunch of cool stuff, and we're going to be working with it for the rest of the year, like the entire rest of this class. It is unimodal and symmetric. It is sometimes called a bell curve. If you've heard of a bell curve, it's because it kind of looks like a bell, I guess. It has a mean of mu and a standard deviation of sigma. So this is the Greek letter mu, and this is the Greek letter sigma. You may remember that this is also the Greek letter sigma. This is a capital sigma, and this is a lowercase sigma. It has tails that extend infinitely in both directions. So these are the tails. Many variables are nearly normal. None are exactly normal. Oftentimes we're going to treat things as if they are exactly normal, but when you're describing a distribution on the AP test, you should say that it's approximately normal or nearly normal. Don't ever just say that it's normal. They don't like that. They take points off for that. So for normal distributions, we have something called the empirical rule, also known as the 68, 95, 99.7 rule. So for data that are approximately normally distributed, about 68% falls within plus or minus 1 standard deviation of the mean. So since a normal distribution is symmetric, the mean, the median, and the mode are all the same number. And so minus 1 standard deviation to plus 1 standard deviation, that's going to be about 68% of your data. About 95% of your data is within minus 2 standard deviations to plus 2 standard deviations. And then nearly all of it, about 99.7%, is within plus or minus 3 standard deviations. So if you remember this, you can figure out, just using some basic arithmetic, what percentage of the data fall within any of these whole number standard deviations, right? So if I want to know, what percentage of the data are within minus 2 standard deviations to minus 1 standard deviation, right? So I know that 50% of the data is to this, is less than the mean and median, right? If 68% is plus or minus 1 standard deviation, that means that this is going to be 34% on each side. If 95% is plus or minus 2 standard deviations, 95 minus 68 would be 22? 70, no, 27. 27. Would be 27, that's in both of these blocks. That's within 2 standard deviations, but not in this middle part. And then if I divide that in half, that's 13.5% that's in this block that I originally wanted to find. So if you remember the empirical rule, you can use some arithmetic to find specifically within these whole number standard deviations. If we want to find a a score for a part of a standard deviation, we have to use z-scores, and we have to use either a z-score table or a calculator. So looking at this number of hours of sleep on school nights, the data appear to be approximately normally distributed. Obviously, this is not a continuous, or when people reported their numbers, they did not report all the values between 4 and 9. You've got a lot of people that are reporting, looks like probably whole number values, rather than half number values. So that's why you've got these peaks here. But we can pretend that it is approximately normally distributed, with a mean of 6.88 and a standard deviation of 0.93. And so this, you can calculate, you would have a calculator or a computer calculate it for you. 72% of the data are within plus or minus 1 standard deviation of the mean, right? So plus one standard deviation, 6.88, plus 0.93 is going to be, carry the 1, 7.81. And 6.88 minus 0.93 is going to be 5.95. So between 5.95 and 7.81, you get 72% of your data. And that is taken from the data set. So what they did was they calculated 6.88 plus 1 standard deviation and minus 1 standard deviation, and then looked at the data set to see what percentage of the data fall within there. Within 2 standard deviations of the mean. So 2 times 0.93 would be 1.86. So 6.88 plus 1.86 is going to be 8.74. And 6.88 minus 1.86 is going to be 5.02. So within from 5.02 hours to 8.74 hours, if you look at the data set, you get 92% of the data within there. And then within plus or minus 3 standard deviations of the mean, I don't know why this is not right, 3 standard deviations of the mean would be 99% of your data. So compared to the empirical rule, 68, 95, 99.7, it's pretty close. You've got a little bit more within 1 standard deviation and a little bit less within 2 standard deviations. But, pretty close to normal. So one way that you can check normality is to check what percentage of your data fall within 1, 2, or 3 standard deviations of the mean, and see how that compares to the empirical rule. And just as a note, when we say within 1 standard deviation or within 2 standard deviations, that always means 1 or 2, respectively, to each side. If I'm specifying only above or only below, I'll say within 1 standard deviation above or 1 below. But when I just say within 1 standard deviation, that means 1 on each side of the mean. Okay, so SAT scores are distributed nearly normally with a mean of 1,500 and standard deviation of 300. This is true, by the way. Most standardized tests, like the SAT, are designed so that the scores are distributed normally. When they try out new test questions, they design the test so that the scores follow this distribution. So, nearly normally with a mean of 1,500 and standard deviation of 300. So, 68% of students are going to score within plus or minus 1 standard deviation of the mean. So, 1500 plus or minus 300 is going to be from 1200 to 1800. Right? Within plus or minus 2 standard deviations is going to be 1500 plus or minus 600, which would be from 9 to 21. And then 15 plus or minus 3 standard deviations would be plus or minus 900, which would be from 600 to 2400. And this would be an approximate graph of the normal distribution of SAT scores. This was from back when the SAT was out of 2400 instead of out of 1600. It was for a little bit, and then they switched it back to being out of 1600 now, I think. But so if it's out of 1600, the mean is going to be 1,000, and the standard deviation would be 200 instead of 300, and it all scales down. So when we're describing the parameters of a normal distribution, we're going to write a normal distribution as n mu sigma. So if I say n 5, 1.5, that means a normal distribution with a mean of 5 and a standard deviation of 1.5. So normally distributed, right? So notice how these are the same shape, even though they have different means and they have different standard deviations. We still marked out 1, 2, and 3 standard deviations. Now, if we put them on the same scale, right, this has a mean of 0 and a standard deviation of 1, so 3 standard deviations takes it to 3. Whereas this has a mean of 19 and a standard deviation of 4, so plus 3 standard deviations is 31, and minus would be 7. So when you're sketching it, because we're going to be sketching a whole lot of normal distributions, when you're sketching it, you just probably are just going to, sketch a curve and then mark it out like this. Very rarely are you going to have to actually draw normal distributions to scale. So the standard normal curve is a normal distribution with a mean of 0 and a standard deviation of 1. And we use the normal curve because before we had calculators, you had to use something called a distribution table. And the distribution tables were calculated using calculus. It involves integrating a stupidly complicated function. If you don't know what that means, don't worry about it. But if you're in calculus, ask Miss Madiker how to integrate the normal distribution function. She knows how to do it. But where was I going with that? So as we see here, right, different normal distributions are different shapes depending on their mean and their standard deviation. And so if you wanted to find, say, the percentage of this distribution that's higher than 25, you would need a different table than if you wanted to find the percentage of this distribution that's higher than 25. It's going to be basically 0 for this one, but you get the idea. So rather than having to calculate separate tables for every distribution with a different mean and standard deviation, we normalize the distribution. So regardless of what our mean and our standard deviation are, we can make some adjustments to treat it like it's a standard normal distribution, and then we only have to have one distribution table. Nowadays, your calculator can calculate things can calculate the percentage under the curve with any mean and standard deviation. But what it does is it's normalizing the distribution for you and then comparing it to a built-in table of normal distributions. It's not actually probably doing the integral every time. So the units on the horizontal axis of a standard normal curve are called z-scores. So the z-score is the number of standard deviations away from the mean. So here's our SAT scores. Again, we're using the 600 to 2400 scale for the SAT. Sorry about that. I always think I should go back and change that. Doesn't matter though. So SAT scores are distributed nearly normally with a mean of 1500 and a standard deviation of 300. ACT scores are distributed nearly normally with a mean of 21 and a standard deviation of 5. A college admissions officer wants to determine which of two applicants scored better on their standardized test with respect to the other test takers. Pam, who earned an 1800 on her SAT, or Jim, who scored a 24 on his ACT. So here's a sketch, and you may be able to tell, looking at the sketch, who scored better. But we can figure it out using z-scores, right? We can't just compare Pam's 1800 to Jim's 24 because they're on totally different scales. So instead, we compare their z-scores, which is how many standard deviations beyond the mean their raw score is. So the formula for a z-score is x bar minus mu, or we'll just do x, it's not x bar right now, x minus mu over sigma. The x bar comes in later. X minus mu over sigma. So x is your data point, mu is the mean, and sigma is the standard deviation. So Pam's z-score, right, the x would be 1800, the mean of the SAT distribution was 1500, and the standard deviation was 300. So that ends up being 300 over 300, which is 1. She's 1 standard deviation above the mean. Jim's z-score is 24 minus 21, which is the standard the mean of the ACT distribution, over 5, the standard deviation for the ACT distribution, which is 0.6. So he's 0.6 standard deviations above the mean. Pam is 1 standard deviation above the mean. Pam did better. She's farther from the mean. When we standardize these by putting them on the same scale, Pam did better. So, z-score is the number of standard deviations a number falls above or below the mean. Z-scores are defined for distributions of any shape, but we can only use the z-scores to calculate percentiles when z-scores are when the distribution is nearly normal. Any distribution will have z-scores in that it has a standard deviation, and you can calculate how many standard deviations something is above the mean. But with normal distributions, we can calculate percentiles. Observations that are more than 2 standard deviations from the mean are considered unusual. So that was one of our definitions for outliers. An outlier can be defined as an observation that is more than 2 standard deviations away from the mean. All right, so I want you to practice converting to z-scores. I will show you how to make your calculator do it for you in a little bit, but we are going to start by doing the conversion by hand, and then use the calculator to find the area under the curve. This is calculus, really hard calculus. Okay, so finding areas under the curve. The probability that z, so this is probability notation, which we're going to be talking about more in the next unit, but this is the probability that z is less than -1, which is going to correspond to the area in the chunk of the curve that is less than -1, right? The total area of the curve equals 1. So the probability of a value being less than -1 under the curve is going to be the area of all the parts less than -1. So this one, because it's a whole number, we could do using our empirical rule. We're not going to, though. We're going to do this on your calculator. So on your calculator, you're going to have something that says, you're going to press the button that's right above that says vars. So, let's see if this is going to mess up my recording. It's probably fine. Right, so the button is here, right? So right above, if I press second, where it says distribution, here, the vars button, I want that distribution. I'm going to press distribution, and I want number 2, the normal CDF. We never use the normal PDF. You don't need to know what the normal PDF does. We never use it. It's always going to be normal CDF. Okay? And so, because I'm using my app, it tells me here I need the lower value, the upper value, and the mean and the standard deviation. If you don't put a mean and a standard deviation, it's going to assume that you're using the standard normal with a mean of 0 and a standard deviation of 1. Your calculator may look a little bit different. If you've got a new calculator, it's going to give you the wizard, which is the little screen that pops up, and it'll ask you for the lower, the upper, and the mean and the standard deviation. For right now, because we're calculating z-scores, keep your mean at 0 and your standard deviation at 1. I will tell you when it's okay to change that. But for right now, always have your mean be 0 and your standard deviation be 1. So in this case, I want the lower, I want everything less than -1, right? 1 standard deviation below the mean. So in the tails continue to infinity, right? The tails continue to negative and positive infinity. Calculator doesn't have an infinity for doing something. So what we do is we just put a really big negative number for our lower bound. The one that I usually do is this, except I need it to be negative. Yeah. Right? So 1e, so that E button is this button right here under the sign. If you do second and then do that. And so that means basically -1 with 99 zeros, or 10 to the 99th power, which is a really huge negative number. Basically negative infinity for our purposes. And then I want to go from there to -1. And I'll go ahead and put in my mean is 0, my standard deviation is 1. And I get 0.158. 3 decimal places is good. Your z-score table would usually do 4 decimal places. So compare that to the empirical rule. So we got 0.1586. Using the empirical rule, right, 68% of our data is within plus or minus 1 standard deviation. So everything outside of this is going to be 100 minus 68, which is 32. That's split evenly between the two tails, 16%, compared to this, which was 15.86%. Now, we can't use the empirical rule for numbers that aren't integers. So, again, we're going to use this. Calculator time, right? So, second, distribution, normal CDF. And I want this to be -1 E99 and -1.5. And I'm actually not going to do the mean and the standard deviation because it's going to assume that the mean is 0 and the standard deviation is 1 if I don't specify. And so I get 0.066. Okay? If I want to find the probability of something that is greater than 2.1, so that part, I'm going to do the same thing. But now, because I want greater than 2.1, 2.1 is my lower bound. I'm going to do 1 E99 for my upper bound. .17860178. And then I can also do it to find between two numbers if I want some middle amount. Right, so between -1.2 and +2.1, I want to find this amount. I just use those as my lower and upper bounds. Right, so -1.2, +2.1, and its standard deviation is 0 and 1, 86.7%. The percentile is the percentage of observations that fall below a given data point. Graphically, percentile is the area below the probability distribution curve to the left of that observation. Right? So it's all this shaded area. The percentage of the observations that are below a certain point. Right? So what z-score corresponds to the 50th percentile. Where do you have 50% of your data less than or equal to this point? It's 0, right? The mean is your median in a normal distribution. So your z-score 50th percentile would be 0. Now, for numbers other than 50, we're going to need to use the calculator. So we want to know what z-score corresponds to the 20th percentile, right? So we want to know what some part of, it's actually going to be like here, somewhere between -1 and 0, but corresponds to 20% of the data less than or equal to that point. So, what number is that? Calculator time. So, again, under distribution, right under your normal CDF, you have the inverse norm. That's what we want. And so your arguments are probability and mu and sigma. And so this is always going to give you that left-hand side, just like the picture shows. If you have a newer calculator, the wizard may give you the option of left, center, and right. For right now, pick left. So I want the probability, I want to find the lower 20%. I'm going to put in 0.2. Your probability should always be a decimal between 0 and 1. And I can make my mean be 0 and my standard deviation be 1. Again, we can change that later, but for right now, keep your mean at 0 and your standard deviation at 1 until you actually figure out what you're doing here. So I hit enter, and this gives me the z-score that corresponds to the lower 20% of the data. What happened there? Sorry, let me try that again. 2, 0, 1. I accidentally hit something, I think. There we go. I was like, that didn't seem right. Right, so this gives me the z-score that corresponds to the lower 20% of the data, negative 0.84, which is between 0 and negative 1, which is what I told you it was going to be. This was negative 0.8. Right, so that would correspond to this right here. Now, if we want the part with the upper 70%, all right, we want 70% above it. If you have a newer calculator, you can just put the area to be 70, or 0.7. I hate it when I put the area to be 0.7, and just leave the mean on the standard deviation and pick right. And that would give you the upper area instead of the lower area. My calculator doesn't have that fancy little wizard, so what I need to do is a little bit of quick arithmetic. If I want 70% of the data here, but my calculator only gives me the lower part, so what percentage would be the lower part if the upper part is 70%? Well, it would be 30%. So instead, because my calculator only gives me the left side, I'm going to use 30 because that corresponds to a right side of 70. So distribution, inverse normal, and I do 30 and hit enter. Right, and so that gives me a standard z-score of negative 0.52. And if you have a calculator that has the left, right, center, if you do 0.7 and do the right, you should also get the same z-score. Go ahead and try it. At the Heinz Ketchup Factory, the amounts which go into bottles of ketchup are supposed to be normally distributed with a mean of 36 ounces and a standard deviation of 0.11 ounces. If the amount of ketchup in the bottle is below 35.8 ounces, then the bottle fails the quality control inspection. What is the probability that a randomly selected bottle fails the quality control? That is, what percentage of bottles fail quality control? So, always helpful to sketch a normal curve. You'll get really good at drawing that normal curve there, with a mean of 36 and a standard deviation of 0.11. We want, if the amount in the bottle is below 35.8, so here would be 35.8, and we want to know what goes in here, right? So we want to find the area under the curve for being less than 35.8. So our mean is 36, our sigma is 0.11, And we want the probability that x being a randomly the amount of ketchup in a randomly selected bottle, is less than 35.8. Get used to this probability notation. We're going to be using it a lot. So, calculator, right? Well, actually, before I do that, right? So find the z-score, right? Is x minus mu over sigma. So our x is 35.8. Our mu is 36. Our sigma is 0.11. 35.8 minus 36 over 0.11. Negative 1.8181. Let's just call it 818. Okay? So that's our z-score. So now, calculator time, use the normal distribution. So second distribution, normal CDF. We want less than that, so our lower bound is negative 1 E99. Our upper bound is negative 1.818. And leave our mean and standard deviation at 0 and 1. When we find the z-score, we leave our mean at 0 and our standard deviation at 1. And so we're going to find that the area under that curve is 0.0345. .4%. So, find the z-score. 35.8 minus 36 over 0.11. Right, x minus mu over sigma. And then use your calculator to calculate that area. If the amount of ketchup in a bottle is below 35.8 or above 36.2, then the bottle fails the quality control inspection. What percent of bottles pass the quality control inspection? So, mean of 36, this is 35.8, this is 36.2, right? The z-score was negative 1.818. Z-score for this, right, is going to be 36.2 minus 36 over 0.11, which I can tell you is going to be positive 1.818. So then, use the calculator to give me the normal distribution from negative 1.818 to positive 1.818. 93%. 93.1%. Because the distribution is symmetric, we could also use this being 3.4%, meaning this is also 3.4%, and algebra this, and it should also be 93 point something percent. Body temperature of healthy humans are distributed nearly normally with mean of 98.2 and a standard deviation of 0.73 degrees Fahrenheit. What is the cutoff for the lowest 3% of human body temperatures? So, we want the lowest 3%. We're going to use the calculator, and we're going to do that inverse normal function with a probability of 0.03, 3%. Leave the mean at 0 and the standard deviation at 1. Hit enter. Gives me a z-score of negative 1.88. So my z-score is negative 1.88. Use the z equals x minus mu over sigma to solve for x now. So z is negative 1.88. We're solving for x. Mu is 98.2 and sigma is 0.73. Solve this for x. So 1.88 times 0.73 is negative 1.3724 equals x minus 98.2. Add 98.2 to both sides. And that gets you 96.83. Is the cutoff for the lowest 3%. What is the cutoff for the highest 10% of human body temperatures? So if you've got the left, right, center, you can do area be 0.1 and pick right. I don't have that, so I'm going to do what corresponds to the lower 90% because that's the same as the upper 10%. Second, distribution, inverse norm, 0.9. 1.28. That's my z-score. Equals x minus 98.2 over 0.73. And solve for x. It's 99.1. Which of the following is false? Majority of z-scores in a right-skewed distribution are negative. In a skewed distribution, the z-score of the mean might be different than 0. For a normal distribution, IQR is less than 2 times the standard deviation. Z-scores are helpful for determining how unusual a data point is compared to the rest of the data in the distribution. So, that's true. Right, in a right-skewed distribution, the mean is going to be higher than the median. So, more than 50% of your data are below the mean. Z-scores are standard deviations away from the mean, so that one is true. Right? You're going to have more data below the mean than above the mean. In a skewed distribution, the z-score of the mean might be different than 0. That is false. Z-score is always the number of standard deviations away from the mean, so the z-score of the mean is always 0, regardless of the shape of the distribution. And then for 3, we can sketch this out using our empirical rule, right? 2 standard deviations encompasses the middle 95% of the data. But the IQR encompasses the middle 50% of the data. So the IQR is going to be less than 2 standard deviations away. Real quick, you have this thing called a normal probability plot. We're not going to go over it in depth, but you may see it on the AP test. Hopefully not. But what they do is they take all of the data points and find how far away they are from, how many standard deviations they are away from the mean, and they plot all of those. And if your distribution is normal, it should form a line like this. Alright, so normal probability plot, data are plotted on the y-axis of a normal probability plot, and the theoretical quantiles forming a normal distribution on the x-axis. If there's a linear relationship on the plot, the data follow a nearly normal distribution. Constructing a normal probability plot requires calculating percentiles and corresponding z-scores, which we're not going to do by hand. If you see this on the AP test, they're going to give you a normal probability plot and ask you to interpret it. They're not going to require you to make one by hand. Right? So here you have these, the ones that correspond to these theoretical, so ones that are one standard deviation below the mean are at 75. Here you've got some more points that are in the middle, and then you've got fewer points that are, you've got points that are below the curve there. The points on the normal probability have jumps because height is reported in inches. Even though height is a continuous variable, nobody says that their height is 73.8827 inches. For right-skewed data, your points are going to bend up at the end. Left-skewed data, they bend down at the beginning. If you have short tails, your distribution is narrower than a normal distribution. You're going to get something kind of S-shaped. And if you have long tails, you get something like this. That's a line, but off of the trend line. I guess kind of S-shaped. Lightning bolt shaped, backward S-shaped. I don't know what that is. Anyways, that's the normal distribution. Like I said, we're going to be doing a lot with it for the entire rest of the class. So it's super duper important. I hope you learned something.